All right, so today we're going to dive into some pretty mind-bending science coming out of ETH Zurich. They've basically figured out a way to look at electron interactions within materials in a totally new way. For those listening, this could really help us unlock some huge mysteries in physics.
Huge. Yeah. And I mean, everyone loves a good mystery, right?
Oh, for sure.
And this is a pretty elegant approach to solving one of the biggest ones out there. You see electron interactions. They're like these fundamental forces behind so many crazy phenomena. One of the most famous ones being superconductivity. That perfect flow of electricity without any loss.
But as you can probably guess, getting a clear picture of these electron interactions is super tough. I mean, they're often really weak and super easily masked by other things happening within a material. So the traditional method for, making these interactions easier to study has involved using what are called moiré materials. Think of it kind of like taking, these super thin layers of atoms and stacking them with like a little twist. So that twist, it creates like this interference pattern. Technically, it's called a superlattice. And it's a new, larger repeating pattern on top of the original like atomic structure. And this can kind of have this effect of, slowing down the electrons and then making their interactions a bit more pronounced.
And easier to observe.
But if you're really trying to isolate the electron interactions, this physical alteration of the material itself can kind of create other complications.
Yeah, it's like trying to listen to like a single instrument in an orchestra and someone keeps like retuning all the other instruments.
It's just a mess.
Total mess, yeah.
So the innovation from ETH Zurich offers this way around that.
They figured out how to create, what we can think of as like an artificial crystal lattice within a semiconductor material, but they do it using an external influence. So they don't have to physically change the semiconductor structure.
It's like remote control for electrons.
Yeah, like you're manipulating them from a distance.
Exactly. And for those of you who are really into the nitty-gritty of materials science, what's so important here is this ability to influence the electrons without directly modifying the, underlying atomic arrangement of the material itself that we want to study. It gives us this way cleaner way to actually probe these subtle interactions.
So for our deep dive today, the big question is, how are they pulling this off? And then, what could the ripple effects be for our understanding of, everything from basic materials to these really wild concepts like superconductivity?
For sure. Let's get into it. So how do they actually create these specialized moiré materials that they're using as their remote control?
Well, the magic kind of starts with two super thin layers of hexagonal boron nitride, or HBN.
HBN.
Now, just so you can picture this HBN, it's a material where the atoms are arranged in this super regular repeating honeycomb pattern, much like graphene, actually.
Gotcha.
And this structure gives it some pretty unique electrical properties. The researchers take these two layers. Each one is just a single atom thick.
Wow.
And they stack them.
Okay.
The key thing here, the crucial step, is that they twist one layer just slightly relative to the other by an angle of, less than 2 degrees.
Okay, so it's like you're taking two sheets of that honeycomb pattern and rotating one, just like a tiny bit.
Tiny little bit, yeah.
What's the result of that little twist?
Well, think about when you hear two musical notes that are very close in pitch. You don't actually hear two distinct notes. You hear this wavering sound. It's this rhythmic pulsing. That's called a beating effect. And a similar thing happens when you twist these boron nitride layers. They're slightly misaligned honeycomb lattices kind of interfere with each other, and they create this new, larger repeating pattern. That's the superlattice we talked about earlier.
Right.
And it has a much larger distance between its repeating units compared to the, original tiny atomic lattices.
So it's like for the electrons, they suddenly have this like much bigger playground to run around in.
Yeah.
With this new set of rules.
Yeah, but here's where it gets really interesting. This twisted boron nitride doesn't just create a geometric pattern. It also creates a periodic electric field. To try to visualize this, think of it like a repeating pattern of electrical hills and valleys emanating from the twisted boron nitride. And this field, it extends outwards beyond the boron nitride material itself.
So it's kind of like the superlattice is broadcasting an electrical signal into the space around it.
It's like a projector, casting an electrical pattern.
Okay, and this is where the other material, semiconductor, comes in.
Exactly.
So tell us about that.
Okay, so Directly beneath this twisted boron nitride, the researchers place a single atomic layer of a semiconductor called molybdenum diselenide, or MOS2.
MOS2.
Now, the key breakthrough here is that this periodic electric field, those electrical hills and valleys we just talked about, interacts directly with the electrons in that molybdenum diselenide layer.
Okay, so the electrical pattern from the boron nitride is kind of like imprinting a new structure onto the behavior of the electrons in the semiconductor, even though they're not physically connected in the same way as they are in like a traditional moiré material.
Absolutely. That's the real innovation here. The electric field from the twisted boron nitride is creating an artificial crystal lattice within the molybdenum diselenide. So those electrons in the semiconductor, they basically feel this new larger framework dictates how they move and interact, all thanks to that external electric field.
Gotcha.
But the arrangement of the molybdenum and selenium atoms in the semiconductor itself remains totally unchanged.
So it's a pretty clever way to get around the limitations of those traditional moiré materials.
Yeah.
So by not physically altering the semiconductor, what advantages does this give them when they're actually studying the electrons?
Well, so the researchers point out a really crucial advantage here.
Sure.
For, those of you who are trying to understand the finer points of condensed matter physics, this electric field, it primarily affects the charged particles, the electrons, within the molybdenum diselenide. It has a much weaker effect on neutral entities called excitons.
Okay.
Now, we'll explain what those are in a second.
Okay.
But the key takeaway is this selectivity. It lets them study the behavior of electrons in this artificial lattice much more cleanly without those confounding factors that arise when the entire material structure is distorted, as is the case in, direct moiré structures.
Okay, so we have our electrons in the semiconductor now behaving as if they're in this new kind of lattice, all thanks to this external electric field. But how did the researchers actually observe what these electrons are doing?
That's the million-dollar question, right?
Yeah.
Well, this is where those excitons come in.
Okay, so tell me about excitons.
Yeah, excitons are this really fantastic tool for probing the electronic state of a material. So think of it like this. When light of a specific energy or frequency strikes the semiconductor, it can give an electron a boost, kicking it up to this higher energy level. And this leaves behind a positively charged hole in its original spot. And because, opposite charges attract this excited electron, and the hole it left behind can briefly pair up. They form this neutral particle called an exciton. It's this temporary bound state of an excited electron and its missing partner.
Gotcha. So shining light basically creates these temporary electron hole pairs within the semiconductor. How does that help them study the behavior of the other electrons that are, being influenced by the artificial lattice?
Okay, so the important thing here is that the energy required to create an exciton, and therefore the specific frequency of light needed, is super sensitive to the energy levels available to the electrons in the material. And these energy levels, in turn, are directly influenced by the artificial crystal lattice created by the twisted boron nitride's electric field.
It's all connected.
Yeah, so by carefully analyzing the precise frequencies of light that cause excitons to form in the molybdenum diselenide, the researchers can indirectly get really detailed information about the behavior and arrangement of the electrons within that artificial lattice.
So it's like studying the ripples on a pond to understand the shape of the stone that was thrown in.
That's a great analogy.
So can you give us a specific example from their research?
Yeah, absolutely.
With what they actually observed using this technique?
So by applying a voltage to their setup, they could carefully control the number of electrons in that molybdenum diselenide layer. What they observed was really remarkable. When they had enough electrons to fill roughly 1/3 or 2/3 of the sites in their artificial lattice, the electrons spontaneously organized themselves into these regular repeating patterns. This kind of self-organization. It's a telltale sign that strong interactions are happening between the electrons.
That's just incredible to think about.
Yeah.
These electrons are arranging themselves based on how many are present.
It's pretty wild.
Yeah. And what happened when they increased the number of electrons?
So when they further increased the number of electrons, so that on average there was more than one electron per lattice site, They saw these distinct shifts in the frequencies of light needed to excite the excitons. And this indicates that, the increased density of electrons was leading to even stronger interactions between them, which in turn altered their fundamental energy states.
So for those of you listening who are really interested in the bigger picture, this is where things get really exciting.
It does.
Because it connects to some of the most mysterious areas of modern physics.
For sure.
Like superconductivity. So how do these findings actually help shed light on these phenomena?
So these insights into how strong electron interactions can lead to these ordered states, they're super valuable in a lot of materials that become superconducting when extra electrons are added, in a process called doping. The underlying mechanism is believed to involve these really intricate, strong interactions between those added electrons.
So this new technique gives them a much cleaner, the more controllable platform to study these fundamental interactions so it could help us finally unravel the specific conditions and behaviors that allow electrons to pair up and flow without any resistance in superconductors.
And that's the holy grail, right?
Yeah. So by being able to essentially watch how electrons organize themselves in this artificial lattice, we might be able to get some really crucial clues about how they team up to achieve that superconductivity.
It's like we're getting a peek behind the curtain at this amazing quantum dance.
Yeah. And what's really cool is that the researchers are saying this method offers a lot of control.
Oh, yeah, a ton.
Like just by adding or changing the number of layers in their stack of materials, they can actually fine-tune the strength of the electric field that's creating the artificial lattice. So this tunability opens up so many possibilities for, precisely manipulating those electron interactions. So beyond superconductivity, what other potential future applications are they excited about?
Well, one really cool avenue is studying processes where electrons don't just interact within a single layer, but can actually move between different layers in a multi-layered structure. And the researchers suggest that in that kind of situation, an electron could get this internal pseudospin. Yeah, depending on which layer it's in. This could pave the way for probing some really exotic phenomena that haven't really been seen experimentally, like chiral spin liquids.
Chiral spin liquids.
These are theoretical states of matter with really unusual magnetic properties.
Yeah, those sound super futuristic. And the fact that they haven't even been observed yet makes this research even more exciting.
Yeah, it's like we're on the cusp of discovering something completely new.
And what's amazing is that the potential of this technique is huge. I mean, it's not just limited to boron nitride and molybdenum diselenide. In principle, this approach of using one material to remotely engineer the electronic environment in another could be adapted to study electron interactions in a whole bunch of other materials, which could lead to breakthroughs in all sorts of areas.
Totally.
So let's bring it all together for you. In this deep dive, we've explored this cutting-edge technique from ETH Zurich, where scientists are using twisted layers of boron nitride to generate a periodic electric field, and this field then acts on the electrons. In a separate semiconductor layer, molybdenum diselenide, effectively creating an artificial crystal lattice, but without physically altering the semiconductor structure.
It's pretty ingenious.
And by carefully observing how these light-induced electron hole pairs, exciton, behave within this artificial lattice, the researchers can get these unprecedented insights into electron interactions.
Yeah, and it's such a cleaner way to investigate some really fundamental physics.
And this holds so much promise for understanding and maybe even manipulating these really exotic electronic states, maybe even leading to the discovery of entirely new phenomena. And what really stands out here is just like the precision and the level of control this method offers. Like it really lets us isolate and study electron interactions in a way that just wasn't possible before.
Yeah, we're opening up this whole new window into the quantum behavior of materials.
Which brings us to something really fascinating for you, our listener. Think about how the ability to precisely control and study electron interactions at such a fundamental level,
at such a tiny scale,
could revolutionize material science. Like what kind of new possibilities might emerge if we could really harness the behavior of electrons in this way?
It's mind-blowing to think about.
Yeah, and it just goes to show how pushing the boundaries of our understanding at the smallest scales can have these really profound and unexpected consequences for the world around us. So this has been a deep dive into the fascinating world controlling electrons with twisted boron nitride layers.
Some pretty cool stuff.
And if you found this journey, as mind-bending as we did, be sure to like and subscribe for more deep dives into the, ever-evolving landscape of science. And let us know in the comments below what other scientific topics you're curious about.
Yeah, what do you want to explore next?
Stay tuned for our next exploration into the wonders of the universe.
See you then.
Bye.
Yeah.